Hey friends, welcome to the YouTube channel all about electronics. So in this question, for the addition of the two 16-bit numbers, this 16-bit ripple carry adder has been designed and it is designed using the half adders and the OR gates. So here, we have been asked to find the number of half adders and the OR gates which is required in this design. So recently, we have already covered the video on the ripple carry adder and we have seen that by cascading the n full adders, we can design the n bit adder. So here, let us take the example of the 4 bit adder. So just by cascading the 4 full adders, we can design this 4 bit adder. But here if you observe, then when we are adding the two LSBs of the 4 bit numbers, then the incoming carry is already equal to 0. And since there is no incoming carry, so we can do this addition even using the half adder. That means we can design this 4-bit ripple carry adder using the 3 full adders and 1 half adder, where this half adder can be used for the addition of the LSBs. So in general we can say that this n-bit ripple carry adder can be designed using the n-1 full adders and 1 half adder. Now earlier we have also seen that this full adder can be designed using the 2 half adders and 1 OR gate. That means when we are designing the n-bit adder, then in this design, we can replace the each full adder with the 2 half adders and 1 OR gate. So we can say that for the n-bit addition, we require 2n-2 half adders and n-1 OR gates. And this 1 half adder is required for the addition of the LSB. That means for the n-bit addition, we require total 2n-1 half adders and n-1 OR gates. So now, if we take the case of the 16-bit adder, then in this equation, this n is equal to 16. That means for the 16-bit addition, we require total 31 half adders and 15 OR gates. And therefore, for the given question, this C is the correct answer. Alright, so now let's move to the next example. So in this example, we have been given that the 1-bit full adder takes 20 nanosecond to generate the carry bit and it takes the 40 nanosecond to generate the sum bit. And here, by cascading 4 such 1-bit adders, the 4-bit adder has been designed. So here, we have been asked to find the maximum rate at which this 4-bit adder can perform the additions. So here, we have been given that this 1-bit full adder generates the carry bit in 20 nanosecond while it generates the sum bit in the 40 nanoseconds. And here we do not know the internal circuit of this full adder. But using such 4 1-bit adders, this 4-bit adder has been designed. So in this question, for calculating the maximum rate of addition, first of all we need to find the worst case delay of this 4-bit adder. And to find that, let us see how the carry is propagating from the first stage to the last stage. So as soon as the input bits are applied, then this first full adder will generate the sum bit in 40 nanosecond while it will generate the carry bit in 20 nanosecond. That means the valid carry to this FA1 will be available after 20 nanosecond. And as soon as this valid carry input is available, then it will generate its sum output after 40 nanosecond. That means this S1 will be available after this 20 plus 40 nanosecond, that is equal to 16 nanosecond, while this C2 will be generated after 20 nanosecond. That means as soon as this C1 is available, then this C2 will be available after 20 more nanoseconds. Or in other words, it will available at the 40 nanosecond. Now as soon as this C2 is available, then this C3 will get generated after 20 more nanoseconds. That means it will be available at the 60 nanoseconds, while this S2 will be available at 40 plus 40 nanosecond, that is equal to 80 nanoseconds. Now as soon as this C3 is available, then this C4 will be available after 20 more nanoseconds, that is equal to 80 nanoseconds. And likewise, this S3 will be available after these 60 plus 40 nanoseconds, that is equal to 100 nanoseconds. So let's say the propagation delay for generating this carry bit is equal to Tc, while the propagation delay for generating the sum bit is equal to Ts. That means here this Tc4 is available at 4 times Tc time, while this Ts3 is available at 3 times Tc plus Ts time. Or in general, for the n bit adder, we can say that this time is equal to n times Tc, while this Tsn is available at n minus 1 times Tc plus Ts. That means for this 4-bit adder, in the worst case, the stable output will be available after 100 nanosecond, and after that delay only, we can start performing the next addition. That means the rate of addition is equal to this 1 divided by t, that is equal to 1 divided by 100 nanosecond, and that is equal to 10 to the power 7. That means the maximum rate of addition for this given 4-bit adder is equal to 10 to the power 7, and hence for the given question this D is the correct answer.